Sorry guys, I've just been really crook. Oh, I just recorded blowing my nose. Okay, right, let's get started. Essentially, what we tried to look at last time was the motivation behind IPv6. One of the reasons was that the addresses, 32-bit addresses were running out. So, hence IPv6. And where we stopped off was trying to look at, trying to understand the changes in IPv6. And so I had the two protocol diagrams side by side. And wanted you guys to have a look at to see what differences you realized, right, that were on the diagram. So one thing you guys said was there were no options, so that's true. But there are options, but they're implemented in a different way, right? The other thing was somebody mentioned hop limit. It's name correction, I guess, because it's not really a time field. It's a number of hops that you make. So you identified flow label, which is kind of way of defining what kind of traffic is being carried. Is it voice traffic? Is it data traffic? So a certain type of traffic flow can be treated differently, right? So that's one idea. What else did you guys see? Oh, by the way, that was also an exam question, just exactly what I just asked you. What other changes do you see, and why might they be there? What's missing, or what's? Yay, that's right. There's no checksum. Thank you. So this guy's gone. Probably answered this question already, but why might that be okay?
Because TCP UDP already checked it.
That's right. TCP UDP already has a checksum over the entire payload, right? So, and then you'll see, hope we're going to get to do data link layer. You'll see that even the data link layer does error correction. Yeah, I'll do.
But it doesn't have like a checksum for the destination address.
That's right.
So how does it make sure?
So there's a small risk, right? In that what you're saying is, oh, what if some of this stuff gets corrupted, right? So you know, that's left to a lower link layer, right? So you'll see that when you look at the link layer, you'll see that link layer is also doing error correction and detection, right? So why implement all of this at every single layer? Okay, so IP has chosen not to have it, and these days, most of the links are pretty stable, right? You don't get a lot of errors like you used to anymore. Okay, so most of the payload is typically protected. So a decision was made. We don't need to do checksum over the header, so that was removed, right? And that would make things faster, right? Because the checksum is annoying. Why? Why would the checksum be annoying? What happens every time a router processes an IP packet? What does it have to do? In IPv4, what does it do to this field? When a router forwards a packet, yeah, it has to reduce this, right? So if you change this field, what does it have to do then? Recalculate the checksum, and it has to write this packet again, right? So that's a lot of work, right? So you have to do this for every single packet that comes in, right? So now you don't, right? You just change that and send it out. So that reduces the amount of work a router has to do, right? What else did you guys see? What's missing? Come on, missing is easy. You haven't said the most obvious thing. Huh? The length. Okay, that's good. Good, you picked up on that one. So there's a thing called header length here, right? What was I using? I forgot the color coding. I think I was using pink, but. So header length is gone. So what does that tell you about the IPv6 header? Fixed length, right? And why would that be better? It should be obvious, because if you're a router processing packets, you know exactly how many bits to read, right? So you know exactly how much data to take out and process, okay? But if you didn't, then what do you have to do? Think, you're a programmer, right? You'd have to first read up to this, extract this, right, byte, understand what the length is, right, and then figure out, then read the header, right? You don't have to do that anymore. You can just do it in a single step. I know exactly the length of the header, right? So it makes processing much faster, yeah? Come on, there's one more thing that's missing. It's really in your face.
The identifier.
Yeah, it's getting closer. What else? Flag and?
Fragment offset.
Okay, what does that tell you? That's gone, right?
That the IP packet never gets split.
Fragmented, right? So fragmentation is gone, right? So no more fragmentation, right? So IPv6 routers do not fragment packets. Having said that, you can fragment packets if you want to. There's a facility to do that, right? It's an optional header. But by default, there's no fragmentation. So whether you need to, so the determination of the size of the payload is left up to the sender, right? Okay? So the routers are no longer responsible because that's a job that just slows down a router, right? Every time you get a packet, you got to determine the link length. If it's short, I got to fragment, create all these new packets, create all these new headers, create all these checksums, so just too much work for the router. So that's removed. Yeah.
What if one of the router connections down the line can't
Yeah.
support a size as big as the sender is sending in IPv6? What happens?
Yeah, exactly. So the job of figuring out the MTU, right, maximum transmit unit size, is left up to the sender. So there's what's called the MTU discovery protocol, right? So you run an MTU discovery to figure out what is the biggest chunk I can send, right? And based on that, you determine the packet size, right? Okay. So if a router gets something that's too big, and if the fragmentation options are not used, it'll just drop the packet. So it's not my fault. You should have checked, right? So it just makes routing decisions faster, right? Okay. So you don't have that problem with IPv4. So all this stuff is gone. So that just totally simplifies the header, right? It's very straightforward. Okay. You still have payload length. So I told you, although the options are kind of gone from the main header, there is a facility for processing options, which is this pointer here, right? So this pointer actually can point to a bunch of optional header fields that can go just before the payload here, right? But it's no longer part of the header itself, right? So that means I can read this chunk, right, and process it and check if there is more to go, and then read the next chunk, right? Okay? So that's the way options are supported in IPv6, right? Yeah, so that's pretty much what I want to say. The other thing I want to focus, so there's a bunch of slides around IPv6 is what's called, so IPv6, the idea was to support security, so you can have some of the optional headers allow authorization, fragmentation if you really wanted to do it, right? You can have an encrypted payload. There's also a jumbo packet option, which is not here. That is, if you may have a large fiber optic link, I don't know, 10 gigabit link where you can just send a huge packet if you wanted to. So there's a whole bunch of options that are available. I'm not going to go over all that, but I'll let you know that they're there, and you can look up the RFC if you wanted to know more. But I did want you to understand the differences as well as the motivations behind IPv6 and how it was simplified, how it makes routing faster, right? Although you have a large address. Okay, so IPv6 has been around from last time. The idea or the concepts have been since 1990s, right? So we're 2008, 2018, and we're still using IPv4 addresses, right? So why didn't we just go to IPv6? Well, you can't, because there's millions and millions of devices on the internet. You can't just say like, hey guys, tomorrow morning we're just going to change all the stacks and everyone's going to run IPv6. Not going to happen, right? So it needs to be deployed gradually, right? So as a result, we're still transitioning to IPv6, right? Over the last 20 years, we're still transitioning, right? So you might find that when you, if you do a if config or what's the Windows one? ipconfig. Command, you'll find that you actually have an IPv4 and an IPv6 address, right? Okay, so since the 1990s, we're still in a transitioning phase, right? Eventually going to get there. It's hard to just change all networking equipment overnight, to run IPv6. So we need an approach to be able to do this. Typically, you'll come across two approaches. One is what's called the dual stack approach and tunneling, right? So the idea between dual stack is essentially some of the routers will run both IPv4 and IPv6 stack at the same time, right? So there might be networks out there that are just simply IPv6. So here's a, maybe this is an IPv6 only network, right? So here's if you like an IPv4 network, okay? And these guys here will run a dual stack, right? So when it's leaving the IPv6 network, so they will have, that means these routers have a software to talk IPv4 and IPv6. Essentially, the idea is that you take an IPv6 packet and then you convert it to an IPv4 packet and send it down the link, because you know the next destination is an IPv4 router and will not understand IPv6 packets, right? The problem with this should be fairly obvious. If you look at the protocol, you know that the headers don't always match, right? Yeah, not all IPv6 headers match to an IPv6 header. A good example is flow, right? So you see that this is missing in here, right? Because there's no direct match. What's the other obvious problem going from an IPv6 to an IPv4 packet?
The address size is different.
Yeah, address size is different. One's 128 bits. Now I have to map it down to 32-bit. So luckily, people have thought about that. So there are network address translation protocols out there and standards that define how to do that, right? So there's a standard way of how to convert a 128-bit address to a 32-bit address, and then when it arrives on this side, to recover back the 128-bit address, right? Which is what people call network address translation, right? So the problem with this approach is essentially because you have to convert from IPv6 packet to an IPv4, so this is a IPv4 and this is IPv6, you lose information, right? So if you're doing protocol testing, you lose the ability to be able to test your full functionality of your protocol, right? Because you can't support all the functions, right? Okay. The other approach, do you have any questions? The other approach is tunneling. So tunneling is a concept you guys already know about because you use VPN, right? You go home and you want to connect to the university, you may use Cisco VPN client, right? Which essentially creates a secure tunnel, if you like, between your computer and that terminates at the university, right? So you can use the same idea. Okay, so essentially what happens here is that, so you have an IPv6 network here, and this router now knows that this next link is going to end up in IPv4 router. So what it does is it takes this packet, right, puts it as the payload, right? It makes it the payload of an IPv4 packet, right? Oh, wrong color. So it embeds this as a payload of an IPv4 packet. Right? So this is IPv4, and this is your IPv6 packet, right? Okay, so that's tunneling. So the nice thing about tunneling is quite obvious because you're able to preserve the full protocol behavior, right, throughout this link. Because when it gets to the other side, you strip this packet out, and you get your IPv6 packet, which can travel across your IPv6 network, right? So you can have layers and layers of protocols like that, yep.
If you have IPv4 to start off with that goes through IPv6, would you just have the IPv6 in the middle wrap the IPv4, like the same thing?
You can do it the other way around, yeah. Yeah, you can tunnel, absolutely. You can tunnel either way. So the cool thing about this is if you guys are testing a protocol, typically this is what you would do, right? Because you'd want to preserve the behavior of the protocol. So you could tunnel your protocol across another protocol until it gets to the kind of network that understands your protocol, right? So this is tunneling, right? So you might wonder, how does this router know that it's an IPv4 packet? Do you remember what the hook was between the two? there's a field, right? Do you remember what the field is?
Payload protocol.
No, what's it called? This thing, upper layer, right? Defines who to give it to. So there's a special upper layer protocol number which identifies the payload as an IPv4 payload, right? So it hands over to the IPv6 layer, right? Do you have any questions? Because that's pretty much what I want to talk about in terms of IPv6 before we go into link layer. Does this sound good? Do you understand the motivation? Why we haven't got to IPv6 yet? Why we're transitioning, and what are the approaches during the transition phase, right? And why some approaches might be better than others, right? Of course, both are used. All right, so cool. Link layer, yay. So just to kind of go over stuff, we started by talking about networking, but initially what we said was we have an application layer, right? So the application layer, we had something like HTTP, so where we may have a message like hello, and then what the application layer does is put this message inside at some header bits, HTTP headers, right? And then what does it do? This message, when you guys did the web server, is handed over to a?
TCP.
Yeah, that's right. So it goes into a socket, and from the socket, it's given to the transport layer, right? So let's say we use TCP, right? So what happens to TCP layer? So you have your message, you have your header 1, hello, and what does TCP do? TCP will add its own set of headers, right? So this becomes essentially the payload. So what does TCP do? TCP provides end-to-end connectivity between two processes. TCP hands it over to the, what's below? Network layer, right? So what happens at the network layer? IP, let's say internet uses IP, right? So IP goes, so you have your hello, application layer header, TCP header, and you got your IP header, right? So as far as IP goes, this is your payload, right? Okay. So sorry if so this is the payload here, right? So what does the network layer do? What's below the network layer is a link layer. So network layer takes care of how do I take this packet from destination A to destination B, right? Route determination, right? And forwarding. That's a key job, right? So when you sit on your network interface, your card, the wireless interface or wireless card that you have, essentially your operating system has now taken your packet, taken it down these steps, right? Okay? And then the next thing it's going to do is to hand it over to where it needs to get to the physical layer. Eventually it has to get to a wire and turn this into electrical signals, right? Okay, so it's going to go to the link layer, right? So the link layer is responsible for essentially taking this data, right, putting it into what's called a frame and taking across a single link, right, from one to another. So below this is the link layer, right? So what happens in the link layer? So you have your hello, message, HTTP headers, TCP headers, IP headers, link layer headers, right? So for the link layer frame, now we have a fancy name, right? It's now called a frame. This is your payload, right? Okay, so that's your payload. And the link layer is now responsible for taking this packet across a single link. So we're going to look at some of the stuff about the link layer, but you'll see that most of the concepts there are very similar to what we've seen. So but we're going to cover the one thing we hadn't covered specifically, which is about error correction, error detection, right? Which is something that we left for later, okay? So the data link layer is essentially responsible for taking the packet and transferring it, a datagram from one node to a physically adjacent node over a single link, right? Okay. Now, in terms of, this is just stripping out some of the diagrams on your slides. So in terms of terminology, we just at the link layer we call all these things nodes, right? So if you like, and any of these are links. So this is a link, and wireless. This is also a link, but obviously this is air. Like now, you guys using air. Your wireless connection using air. Air is a link, right? We're all sharing air. I'm not, but you guys are probably. I'm not using any wireless links. Okay, so all these are links. So your wired links, wireless links, local area networks, and we have frames at the link layer, right? So just slightly different terminology, right? So frames, essentially, this is a word you might hear, encapsulate. So frames encapsulates datagrams, right? Like I just showed you. Okay, so you have bits that you put on the front, sometimes at the end, and that carries a frame across, right? So that's what that looks like. And so where's the link layer implemented? Typically, the link layer resides between software and hardware, right? So if you look at your network card, they used to look like that, but now they're all integrated onto the motherboard. So we have the application layer, software, transport layers in software, network layers in software, but the link layer is spreading across both the software and the hardware, right? Okay. So the link layer has a controller typically implemented in hardware, right? And then below the link layer is a physical layer. So the physical layer can include wires, right? Electrical signals. So it could be like, how do you represent a 0? How do you represent a 1, etc. Right? Encoding formats. So maybe you've heard of non-return to 0, Manchester coding, whatever, all that kind of stuff. Maybe you heard of amplitude modulation, phase shift keying, whatever, all that kind of stuff is link layer. Sorry, physical layer, which we're not going to talk about. But essentially, the frame from the link layer needs to be turned into some electrical signal, and there are standards for that as well, right? So the link layer is kind of spread across both the software and the hardware, okay? So this is a slide from your pack. Essentially, basically what I went through. So most of the time, here's your host, which takes a packet, and it eventually travels down to the link layer. From the link layer, it's a frame that's handed down to the physical layer, which turns it into ones and zeros. And here's a router, right? So we say routers are layer 3 devices. Why? Because routers, at minimum, need to understand and operate at the network layer. Okay, these days, we talked about software-defined networks before, and we said they can look across multiple layers of protocols, etc. So, this diagram may become redundant, useless after a while, because things are changing. But typically, a router will only need to look at network layer information, right? Okay, and then that's enough to determine its next hop. Then it needs to hand the packet back down to the link layer on the outgoing link, physical layer, blah, 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 right? So this is the link on the in, is the link on the outgoing, right? Incoming link and outgoing link. So this is the forwarding decision, right? For each of those interfaces will have its own link layer. So what you'll notice is that the link layer is just responsible for this part, right? That's it. Okay, that's all it does, nothing else, right? How do I get from one node to another node? That's it. That's its job. Okay. Let's get to something interesting. Okay, we talked about so link layer does framing. Framing means the encapsulation of a datagram, which is just basically what I said before, taking the message from the network layer and putting it inside a frame that you can carry across a link, right? We'll look at link layer. Then if your link layer is wired, then this job is easy because a wire, it's like a piece of string. You put something here, ends up at the other end, right? But if your link layer is like now air, right, there's a problem because it's like all of you guys are talking at the same time as me, and then there's interference, right? Nobody can understand what's going on. So the best way to make that happen is for us to take turns, right, for example. So the link layer also deals with what's called media access control. That is media being air in this example, right? Access control being you and me determining how do we share this space so that we can both understand what we're saying, right? So the link layer also deals with media access control, right? How to share a shared medium, right? Okay? So it does all of that stuff. The link layer also has, hey, guess what? Physical addressing scheme, right? So we have one addressing scheme at IP, right? 32-bit addresses for network interfaces. The link layer also has an addressing scheme, right? Which we'll look at, okay? And this is different to IP addresses, right? Link layer, oh, here's not a surprise. Link layer also does implements reliable delivery between, but this reliable delivery, please note, is between two physically connected devices, right? Okay, this is not like TCP. We're talking about two nodes. Okay, this reliable delivery is between two nodes, right? So how does it do that? We know how to do reliable delivery, right? You have some method of determining if there was an error. If there's an error, you'd ask for retransmission. So you know all the techniques for doing reliable delivery. The only thing we haven't looked at is error detection and error correction, right? Which we're going to look at later. But in terms of how to do reliable delivery, you guys should be experts by now, right? Alternating bit, go back N, TCP, come on, right? You know the whole works, okay? Right. So link layer does reliable delivery as well, which you already know about. Link layer does flow control, no surprise, have the same problem, right, as TCP. You don't want to send too much data because even at the link layer, you've got buffers. You don't want to overrun them, right? So you know about flow control, right? Don't overwhelm the receiver, right? Okay? So link layer does flow control. And we're not going to look at that because you've already looked at flow control in TCP, right? And you know what that means and how that happens in TCP, okay? But the one thing we hadn't looked at so far is this stuff, okay? Error detection and error correction, right? So which is going to be the focus for the link layer part of the course, right? So the new bit that we hadn't really covered is about how do you detect errors and how do you correct errors and what are some of the mechanisms out there, and then maybe do some simple examples of how we do that, right? So just a reminder that, we have looked at this stuff already. So what we're going to focus on is link layer access, which is about how to access a shared medium, and then how to do error detection and correction. Yeah?
If TCP is already doing reliable delivery, why do we also need the link layer to do it?
Yeah.
Rely on TCPs?
Absolutely. You can. Good question. So think about it this way, right? So if you have so here's a host, okay? Here's a host. Here's a network. So TCP is essentially a byte stream between two hosts, right? Yeah. So you send something down here. It gets to here, right? So when does this host know that something went wrong?
Timeout or what?
Well, it has to go all the way there, and the end system has to determine there was an error, right? And then eventually it times out, right? So it takes a round trip time, right? And whatever your timeout interval. But what about a link? Link is like here to your router, right? So if this packet had an error going across this link, right? Okay, and then I could just retransmit. That would be faster, right? Yeah, you don't have to wait for the packet to go all the way across the world to figure out something went wrong, right? If you could just fix it on the link itself. All right, so what does this stuff look like? So if you guys are engineering, or it doesn't really matter, but they probably talk about it more, there's no free lunch, right? Okay, everything has a price. So if you want the ability to detect errors and correct errors, it doesn't come for nothing, right? There's a cost to pay. The cost to pay is you got to put some extra stuff in there to be able to detect and correct errors. You know, redundancy, right? So this is the key word, okay? So we need to create some redundant information that allows us to determine that something went wrong, and if something went wrong, could be corrected, right? So this stuff is called the EDC, or the error detection and correction bit, right? So any error correction code or any error detection and correction code will have some form of redundancy bits that you got to stuff. And they're the ones that allow you to go and fix stuff, right? No free lunch, okay? Error detection is not 100% reliable, simply because these redundant bits can also be corrupted, right? There's no, you don't know, you just don't know, right? Nothing is 100% reliable, but there are certain error correction codes that can give you some guarantees on, you know, maybe 10 to the power minus 9 of a bit error, right, that you can't correct, like so-and-so, right? So there are some guarantees you can get in terms of how reliable you can make, and you know, that's just the way it is, that's, right? And the more reliability you want to ask for, the more redundant information you got to include, right? Okay, so no free lunch, yeah? So large EDC field yields better detection and correction, right? So that's a key thing to remember, okay? So in general, what does that look like? So you have a datagram, and then you take the datagram and you calculate these, you know, redundant information, and you insert that information. So you guys know one of that. You did that in your practical, which is the checksum, right? So checksum is a piece of extra information you calculated, and you put it in the packet, right? Okay, that's what we mean. So example would be your checksum, right? Extra piece of information you calculated, and you put it in to allow you to detect errors, right? Here's an example. It goes down a pipe, but typically the wired links these days are really good. I don't think you get many bit errors, right? But the wireless links can be ugly. I mean, you guys can try running a ping program now. You're using you got your laptops, and see what you get as a percentage of successfully delivered packets. Maybe you might find that you're doing really well because there's a wireless access point potentially up there. So maybe it's not too bad. There's another one? So we're pretty well covered. So you're probably not going to find any issues. But maybe if you're at home and you know, kind of walk outside of your house, and then you might find that your link is not as good as you think, right? So there might be more errors, okay? So this is not a good example here. So essentially, what we have is a link that's prone to errors. Could be interference. So Bluetooth and Wi-Fi, 2.4 gigahertz, exist in the same space. So some Bluetooth devices can interfere with the Wi-Fi channels, right? That's known because they're all sharing the same channel. Sometimes your microwave can interfere with your Wi-Fi channel, right? If you're using 2.4 gigahertz, because the microwaves, that's microwave frequencies, they operate around 3, 4, that kind of range, right? Cordless phones can interfere. So you can get all kinds of errors or interference in your channel, right? This causes some bits to be flipped, maybe, you know, all right? So eventually, your data arrives at the other side, and what you get may not be the same as what you sent, okay? D may not be the same, so this is D prime, may not be equal to D. And who knows, maybe this stuff is changed too. But the goal of error detection is to use this extra information that you used to see if there was an error that's occurred, right? If there's an error, like you guys did with checksum, you chuck it out. But if you use the error detection and correction code, then you might try to see if you can fix the error, right? Because if you can fix it, you don't need to retransmit, right? Good example, I don't know, send a packet from the Pathfinder, is it Curiosity? From Mars to Earth, right? It takes like 14 minutes, 15 minutes or something like that, right? So round trip time might be, I don't know, 30 minutes. So imagine you send a packet using TCP, you go, oh, there's an error. Retransfer, it's going to be another 30 minutes, you know, to go back, come back again. So this is crazy, right? So it might be better in that case to use large amount of redundancy, right? So when you get the packet, you can try to correct it, right? So there are cases where you might not want to have the retransmit, but actually have enough redundant information to be able to try to correct it. Another good one is DVDs and CDs. You guys use CDs? How scratch were they? Oh, are you guys a CD, DVD generation still? You are? Okay. So have you seen really scratched CDs and DVDs? They still work, right? Yeah. You know why they work? Because they have a really, really powerful error detection and correction mechanism called Reed-Solomon codes, right? So they're really cool. I mean, they can collect large, even if you had like a half a track that's scratched, they can correct it, right? And then play it back for you, right? So this stuff is powerful, okay? Let's look at an example, enough talking. So the first thing I want to try and cover is, is the internet checksum, all right? That's what I want to do, okay? And because I'm so organized, I prepared a simple example, which you can try to follow. I'll get a calculator going. How much time do I have? Perfect. Built-in computer. Okay, we can do hexadecimal addition. So you guys know the internet checksum is. Internet checksum allows you to do error correction, or error detection, or error correction and detection. You guys use the checksum. What does it allow you to do? Does it allow you to do error detection, error correction, error detection, correction? Which one? Huh? Just the detection, right? Yeah, you can only do detection. You can't correct it. Okay? So does anyone remember how the internet checksum works? It's the ones complement sum, right? Ones complement of the ones complement sum, right? So how to do ones complement addition? It's kind of simple. So let's forget about this part, right? I want to try to keep it simple here. So so in terms of doing ones complement, say you have a binary number. It's two binary numbers, and you know how to add binary, so that's a 2. I made my life difficult. Let me just make that a 0. So that's a 2, 0, 1 left. That's a 1, 1, that's a 2, 0, 1 left, 1, 1, that's a 2, 1 left, so that's a 3, right? So normally if it was 2's complement, what we do is, this is called the, so this is the carry, or the, and if it's 2's complement, we chuck that out, and turns out you get the right answer. But if it's 1's complement, we need to take this and add it back in, okay? So the final answer is actually 1, 0, 0, 1, right? And then you get the correct answer. So the difference between 2's complement and 1's complement is in 1's complement, you take the carry bit and you add it back in, okay? Yeah? So without going into too much detail, and I could show you that that this works out correctly. So in terms of the internet checksum, I think it's too hard to do the binary ones complement for this example, so it's easy to do the hexadecimal ones complement, right? So, but the method is the same. If you have a carry, you add it back in. So you guys have calculators, hex calculators? You have a laptop, you should have one, right? Who has a laptop? Take it out, or if, yeah, go on. You can even find one online, your keyboard, smart devices, right? So the first thing we're going to do is, I'm going to forget about this stuff because the internet checksum uses 16-bit words, right? So here is a 16-bit word, right? So these are words. There's 16 bits. And again, if you're confused about that, so this is really neat when it comes to hexadecimal numbers, because each hexadecimal number can be represented by using 4 bits, because hex means 2 to the power 6. Sorry, hex means there's 16 is the largest number, right? So we only need 4 bits. So A is a 10 and B is 11. So that's a 8 to 1, right? So 8 to 1, right? And then A is a 10, so that's an 8 2. Okay. So it's very easy to convert hexadecimal numbers to binary numbers, right? All right. So if you want to, so each of these hexadecimal numbers is 4 bits. So 4 times 1, 2, 3, 4, that gives you 16 bits, right? So what I want you guys to do is to first take these two and add them together, right? Okay. Want to try and do that? So hopefully it should be AB, AB, 0, 0, plus FFDE. So let's assume this is the data we want to send. So this gives you 1A, A, DE. Because we're doing one's complement, so we need to take this and add it back in, right? So that becomes, E becomes F. Okay, it's 1, D, A, A. Let's hope I get this right. So these are 16 bits, right? So I need to add that back in. So that's 0, 3, A3, AADF. Where's AADE? Just make sure I'm many plus 1 plus 0, 3, X. Can't see anything. ADF plus 0, 3, A3, AE, A2. So we end up with AE, A2. So no carry this time. So here's the next bit of data. So we add that in, which is 9CF2. Hopefully we end up with this number, plus 9CF2, and that's 457. So there's a carry of 1, which becomes 75, which is the same as this, right? So you end up with, let me just delete that. So you end up with 1, 4, B, 7, 4. So we're doing one's complement hexadecimal. So I need to add that back in. So this becomes 4B75, right? So this is a one's complement sum, okay? This is our, if you like, our message, okay? And this is our checksum field. All right? So what we've done is calculate the one's complement sum over the data, which is what you guys did in your prac. Now we have the checksum, but the checksum is a one's complement of the one's complement sum. So we have to calculate the complement of that. So to calculate the complement of this, so what we need is calculate the one's complement of the one's complement sum. So this is easy to do because you subtract 15 from 5. So you get, because this is base 16 numbers, the maximum you can get is 15. So this is what is it? 6? 10, A. Sorry, so this is an A. 8. B is 11. 15 minus 11 is 4. 4, 15, 11, which is B, right? B48A, right? So let me see if B48A is the one's complement of the one's complement sum, right? So this is essentially your checksum. Okay. So when you want to send your data, what you did was you calculated the checksum and you put it in the checksum field, right? By the way, there are many different algorithms for calculating checksums. This is the one that the internet checksum uses, okay? So what we have is B4 8A, right? So this is now the data that you send across. So if you, oh, sorry guys. I did bring a box of tissues. So if you like, what we have just done is this part, right? Okay, that's that part there, if you like. So this is our redundant information with just checksum. We just stuffed it in there, and now we're going to send it over this link, which may cause errors. We don't know, right? Okay. So what does the receiver do? So the receiver's job is to now check using the extra information that we send. So essentially, what the receiver will get is blah, 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 blah. If nothing has happened, this will be B48A. And then you will realize that, well, without going into too much detail, you know that this part adds up to 4B75, right? Yes? Because we already did that. Nothing has changed. Okay? You agree with me? We just did that right here. We added all this up. We got 4B75, right? So if the receiver does the same addition, the receiver should get 4B. Yeah? You with me? So that means this part at the receiver should become 4B75. And now the receiver will add B48A together. Clearly, what will we get? We'll get FFFF, right? Because 7A plus 5, yeah, so we just get 15, 15, 15, 15. So what's the complement of this? Sorry, guys. So we get FFFF. What's the complement of this? One's complement. Which is the answer somebody gave me. Yeah. So you get a 0, right? So if you get a 0, when you calculate the one's complement sum, one's complement of the one's complement sum over the entire 16-bit words, and you get a 0, you know that nothing has gone wrong. Well, most likely, right? With all probability, nothing has gone wrong. Okay, so that's how checksum works, right? Simple algorithm, but that's what the internet uses, right? And that's what you guys used, right? Something very similar. Okay. So, do you have any questions with that? Yeah.
Why does it use the one complement sum of the one complement of the one?
Oh, really.
Instead of just adding them up, like instead of just summing them without one's complementing.
Yeah, no, very good answer. Very good question. So why doesn't it do 2's complement, right? Computers do 2's complement, right? So the reason is this little trick here. Because in one's complement, you take the carry and you put it at the back. So have you guys heard of little Indian and big Indian machines? Not me Indian, I'm not Indian, but you guys heard of those? That's spelled with an E, Indian. So if you were to run this in big Indian, little Indian machine where the byte order representation was different, right? MSB was at the front or sometimes MSB at the back. If you do one's complement, right? Because you always take this part and wrap it back in, it didn't matter which order you sent this, right? You understand? It didn't matter if I had this at the front and that at the back, right? Okay? So the bit order didn't matter because you always take the carry and add it back in, right? So that means you don't have to deal with the Indianness of the machine, right? So that's why one's complement's used. Okay, because you can read up on big Indian and little Indian machines where sometimes the MSB is here, sometimes the MSB is at the back or the front in the byte, right? Byte or bit, whichever order. But because you always take the overflow and wrap it back in, it didn't matter whether it was the MSB or this was the MSB, right? So it's an elegant solution. Yeah. Go ahead.
But isn't that like presuming that the final sum is palindrome?
No, it doesn't have to be palindrome. So all I'm trying to say is like, say this was, so if it was a big Indian machine, right? So let's say this was, so this is the MSB and this, it had the byte order wrong. let's say, I don't know, let's say this was the carry and this was on the other side. But it didn't matter, right? Because you take this and add it back in, right? And you're going to get the same answer, right? So the order in which you send the bits didn't matter because you wrap it back in